Hey guys, this is Cole Weaver with another episode of Designing Hardware, and I have a new project for you. We're going to build a matrix display out of 700 LEDs. It's going to be a modular design. I'm building only 10 of these modules to see how it goes, but theoretically you can build as many of these modules as you want. They all connect one to each other. The goal here is to have a text scrolling from right to left over all these modules. The firmware for the microcontrollers is unique. That means you can increase the length, the total length of this display by building and adding new modules. There is no need to change the firmware for each module. So I'm going to walk you through the whole design process, starting from this till I get to this. We're going to start with an idea, put it on paper, see how everything works, and then I'm going to show you how I drew the schematic, routed the PCBs, and after I get the PCBs from fabrication, I will start soldering and then ultimately write software for this project. There are three different pieces of software for this project, the firmware for the microcontrollers, and then there's the PC application for sending text over UART. And there's also another application which I wrote to make the font set, the characters for the display. I'll show you everything in a moment. I want to say thank you guys for all the support, getting so much feedback for the last projects, and reading the comments. It's been both motivating and also very interesting. So grab a bite to eat, something to drink, make yourself comfortable, and let's do this. So let me show you how everything works. So we have a bunch of LEDs which we're going to arrange into a matrix, 7 lines by 10 columns. I'm only drawing a couple of them here, but I'm sure you get the idea. Right, so again, we have 7 lines with 10 columns. And now I'm going to connect each anode on a row like this. And then I'm going to connect the cathodes, the negative terminal of each LED on a line, like this. This symbol here means there's no junction here, no connection between these wires. Because if I would draw it like this, it would be confusing. So when you see this, it means one wire jumps over the other. Whenever I explain something you already know, don't be mad, please be patient. I'm trying to explain everything in such a way so that even my grandma can understand it, because there are people who are just starting with electronics and sometimes they're not familiar with everything. Back to our drawing, let's name these lines L1 to L7 and the columns C1 to C10. And now how do we drive all this? I'll show you one way to do it. For each line, we can use an NPN transistor. The emitter is connected to ground. It has a base resistor, and the collector goes to a line. We'll use a microcontroller to drive this. And for the columns, we want to supply positive 5 volts. And we're going to use a PNP transistor this time, polarized through a base resistor with the emitter on 5 volts. And then we're going to supply this through a current limiting resistor to each column. And we're also going to drive this pin from the microcontroller. So we have 7 of this, 1 for each line, 7 times. And 10 of these circuits, 1 for each row. And the thing that drives all these transistors will be our microcontroller. So for 7 lines and 10 columns, we're going to need 17 I/O lines, 7 for the lines, 10 for the columns. We're pulling the reset pin high through a resistor. VCC is 5 volts in this case. We're going to decouple each VCC and analog voltage pin through 100 nanofarad, making sure they're very close to these pins. And then we have our ground pins Probably an analog reference pin. It's good practice to decouple this even if we don't use the ADC. And finally the RX and TX to communicate over UART. And the question is, what microcontroller should we use? Probably an 8-bit will definitely do this job. We just need 17 I/O lines. Hardware UART would be nice because we don't want to start bit banging stuff. And also I decided I don't want to use an external oscillator. So probably an AVR Mega 328P would be great. But I'll go even lower than this. I'll use the Mega 8 microcontroller because I think it can handle the job. Just one more thing to add here, this thing can be built in many different ways. You can use a multiplexer or shift registers, port expanders, and then use a smaller microcontroller. Just giving you some examples here. I only took this approach because it's very easy to understand, I think, for everyone. So after this, I hope you'll have no problem to read this schematic. It looks complicated, but it's not. Everything should be clear now. It's not rocket science. If some of you still have questions here, or if there's something I forgot to explain, ask me in the comment section and I'll get back to you with an answer as soon as I can. You can see the transistors here, 17 transistors on this board, 10 PNP general purpose bipolar transistors for the columns. I used, I think, BC327 here, and for the lines 7 NPN transistors. BC337, they're complementary. Any transistor should do, don't worry too much here. The total current draw of the whole matrix should not exceed 200 milliamps. So that's about 20 milliamps for each column, and a little bit more, about 30 milliamps I think maximum for the lines. And that's a very small current. Just make sure you use the same transistors for all the panels. So this schematic here represents one single panel. There are 70 LEDs, 28 resistors, 17 transistors, 1 microcontroller, 3 decoupling capacitors, ceramic capacitors, 100 nanofarads, and 2 pin headers, 1 on each side. So each panel will interface through these connectors with the panel on its left and the panel on the right side. The PCB is a double copper layer, 100 mm by 100 mm. Let me turn off some of these layers. You can see here the base of each transistor is not routed on the top layer. If I turn on the bottom layer, you can see how everything goes to the microcontroller. The boards are designed to use through-hole components only. It's a great opportunity to learn how to solder. There are almost 2,800 solder joints to be made if you decide to build 10 of these panels. So take your time. Practice is the key to master every art. So I sent these boards to fabrication, and in the meanwhile I started a 3D model piece which will help me to place all the LEDs and all the transistors on the same height. This part looks like a mold, and I took all the necessary dimensions to model this directly from the PCB. It has a detaching part which I'm removing after I soldered the transistors. I try to improve the productivity whenever the steps are repeating. Remember, there are 700 LEDs total on these panels, and everything is soldered manually. It took me about 9 hours to solder all the panels. There are 10 panels, and the total length of the display will be 1 meter, about 40 inches or 3 foot 2. You can sit back and enjoy the next segment where I'm starting to work on these panels. After I finished soldering and cleaning all these boards, I wrote the first piece of software to start testing. This firmware only switches all the LEDs line by line, then column by column, just to make sure that everything works. I also measured the maximum current draw on one of these panels. I will need this piece of information to design the power supply for all this. So the goal here, what I intended to do from the beginning of this project, was to have a text which moves or scrolls from right to left, and when it reaches the last column of a panel, will continue on the next panel. So in theory, I could have 1000 of these panels, and the text will keep scrolling on these panels. Here's how I did this. Each of these panels has 10 columns and 7 lines. So on each column I have 7 LEDs, which I can see as 7 different bits. So I can use one byte to describe the status of each of these columns, which LEDs are on and which ones should be off, right? So I use a byte which I declared, and then I move from column to column and I assign the value of this byte. This happens very fast. In fact, it takes only a few milliseconds to go through all the columns of one panel and to define the state of each LED. I also have a second refresh rate which defines how fast the text is moving, meaning how long will something stay on, how long will be off till the next bit configuration will be written. I'm going to explain this better using the following example. Let's say we only want 1 pixel on the 5th line to be on, and we want to move it from right to left. First, we make sure that all the LEDs are off. Then we write this byte 0000100X to the first column. X means I'm not using the 8-bit of this byte, so it could be 1 or 0. It doesn't matter. All that matters are the first 7 bits. After, let's say, 200 milliseconds, I switch all the LEDs off again, and I write this byte on the next column. And now the pixel should be visible on the second column. So the first refresh rate defines how fast I change the value of all the columns of a panel. If it's too low, it will start to flicker. That's because it will start to become visible that I'm switching on and off these LEDs, and we don't want that. That's why we're moving so fast, so the human eye will not perceive this change. The second refresh rate determines the scrolling speed of the text. How fast is this pixel going from one column to the next? And that's for a single panel. To jump to the next panel, I added another set of instructions. So whenever I write the value for the last column of one panel, I then immediately send this value over UART, and this value will be written on the first column of the second panel, the next cycle. But if we only do this, we will lose whatever value this column was previously holding. So before we write the new value into C1, we copy its content into C2. So you see where this is going. For each panel, C10 will take its new value from C9, C9 from C8, and so on. And C1 will get its new value from the serial buffer, whatever's coming on the UART. This is how the scrolling algorithm works. Once I got this step solved, I then started to work on the actual characters, because now I know how to move a single pixel, but I want to use whole letters and characters on this display. So I defined each character as a matrix of 7 by 5 pixels, and I started to create the fonts. So for the letter A, just to give you an idea how I did this, the matrix for the letter A will look like this. And each one of these characters can be represented using 5 bytes. So I wrote a software application in C# to help me draw all these characters and to convert each one of them into an array of 5 bytes. And I created 96 distinct characters. This took me a while because I drew all of them manually, and then I saved them all in a font file. So basically, if I want to display a simple text like hi, I will start from C1. So C1 will receive the first byte for the letter H. Then I will move this byte to C2 and receive the second byte for H, and so on for all the 5 bytes. Then I send the next 5 bytes for I, and then I send 2 or 3 0 bytes to form a space character, and then lastly I send the next bytes for the exclamation point. And all this time the bytes are moving from right to left, cycling through all the columns until I reach the last column on the last panel. Now we want to send some text to these panels, and I started to write another application for this. This piece of software here connects to the panels over USB. And then I can input a text in this box, and when I press send, a couple of things happen. First, I have a method, a function, which loads the font file with all the characters and their byte conversions. And then it starts splitting this text here into single characters. For each character, it then sends those 5 bytes to the first panel, and it does this until it reaches the last character of this text. Here's how it looks. This software here was just a test. The next step will be to do everything this software does in hardware. We're going to design a controller board for these panels, and this controller will act like a translator between the panels and the outside world. It's going to have a USB connector, so I can use a cable connected to a laptop and then send some text over the USB to the LED panels. It's going to have a Bluetooth module as well. That means any device with Bluetooth capabilities will be able to interface with this. For instance, you can use a smartphone or a tablet to make an announcement on this display. And the last thing, but something I had in mind right from the beginning, I'm going to use a Wi-Fi module too on this controller. And that means if you have a web server, or if you have an application which scrapes websites for information, or something like an RSI newsfeed, something that gets you weather information, stuff like that, even the status of your email, where you have an alarm which trips when someone is approaching. I'm gonna let you guys get creative on this. So the controller will enable me to get any text and put it on this display in any possible way. So there's going to be a part 2 of this video. Make sure to stay tuned. I'm going to show you how I designed the controller, then we're going to build it. We're also going to build a power supply for this, and then I'm going to assemble all the modules and build a nice case for everything. If you didn't subscribe to my channel yet, now it would be a good time to do it. And also, if you liked this video, give it a thumbs up and tell me what you think. Until next time, stay focused and keep designing hardware wherever you are. This is Cole Weaver, signing off.